In the last class, we completed up to jump instructions. If you remember, your short jump has 2 bytes of instruction and your long jump has 3 bytes of instruction. The first byte is the opcode, and the first byte in the opcode is the opcode itself, and the second byte represents the relative address. We also learned how to calculate those relative address, which will be very helpful for today's class also. If you have forgotten, it will be a bit difficult. So try to recall previous class. We need to know how to calculate the relative address as well. Moving forward, so today we will start with call instructions. Alright, so let us discuss the call instruction. Very obvious, it is a control transfer instruction. In fact, your jump is also a control transfer instruction. A control transfer instruction means an instruction which transfers the control to some other line apart from that obvious line. From a particular line, you transfer the control to some other line. That is known as your control transfer instruction. But there is a difference between jump and call. The difference is over here. Your call instruction calls a subroutine, or you can also say a routine. But your jump instruction never calls a subroutine. So what is the meaning of a subroutine? The meaning is, in every subroutine, in order to become a subroutine, the label must end with a return instruction. What is the meaning of the return instruction? The return instruction simply means return to the line from where you have called me, or return to the corresponding line actually from where you have called me. So that is the return function. We will see examples related to return. For the time being, just know that in order to be a subroutine, the label must end with return. In that case, we call that a subroutine. Normally, jump instructions do not call a subroutine. Our call instructions calls a subroutine. Now there are two types of call. One is long call or L call, and another is A call or absolute call. The difference is very obvious. I have written one because the other one is the same thing. Long call is a 3 byte instruction, whereas your A call is a 2 byte instruction. In the long call, the first byte is for opcode and the rest two are for address. So similarly, in case of A call, first byte is the opcode and then the next byte is the address. So this is the only difference. All right, so this is about your long call and your absolute call. Better let us see some examples. I think it will be much clearer when we see the examples. Have you finished writing?
Sir, 1 minute, please.
Sir, can you repeat the difference part again?
The difference is your long call is a 3-byte instruction and A call is a 2-byte instruction. So in long call, the first byte is for the opcode and the rest 2 signifies the address. I mean, where you want to go, where you want to control the transfer. That is for the rest 2 bytes. But in case of absolute call, it is a 2-byte instruction. So first byte will always be for opcode. For address, in absolute call, you have only 1 byte allocation. But in long call, you have 2-byte allocation. So what happens is, in long call, you can jump to any address because you have got 2 bytes to specify the address. But you cannot do that in A call. I mean, it is almost similar to short jump, and L call is almost similar to long jump. Okay, can I move on?
So the address here is like relative address for jump.
No. This is not a relative address. In jump instructions, the address is relative address. But in case of call instruction, the address is the direct address. This is not relative. We will see some examples. It will be much more clearer. I'm going to the next page, okay? This is example 3.8 of the book. If you don't want, you may not write as well because I've already uploaded the soft copy of the book. So if you just pay attention to the class, that will be more than enough. I mean, these examples, whether you want to write or not, it is totally up to you. Okay, let me start explaining. Over here, initially the question is toggle all the bits of port 1. That is the main question. Okay? Toggle all the bits of port 1. We have not yet discussed about ports. We will discuss it in chapter 4. But at least let me introduce you a few things over here. That in your MUSI 8051, we have got a total of 4 ports. We have got a total of 4 ports, and the size of each port, I mean, in each port there are 8 pins. So there are 8 pins in each port. So in total, your 4 ports contain 32 pins. Since each port has got 8 pins, it is known as a byte-sized port. I repeat, each port has 8 pins. That's why it is known as a byte-sized port. Now the question says, write a program to toggle all the bits of port 1. So how can we toggle? So see, first of all, we are sending this value to port 1. Initially, starting with 0, moving 55H. So I have shown you the binary format. We are moving 55H to A, and then we are moving the value of A to P1. In port 1, as I said, we have got 8 pins. So in 8 pins, these values will go. Then after a specific time delay, again you see we have the value 0AAH, that is this value. So after a specific time delay, you are sending this value to port 1. So what is happening? Each of the pin is being toggled to the opposite value. All right. So this is how you toggle the bits of a port. Now let us come to the point that we actually wanted to discuss. That is this lcall. So this is a call instruction, and it is a long call. And as I said, it calls a subroutine. What is the condition of a subroutine? The condition is the subroutine must end with a return instruction. So what happens is, whenever you call this subroutine, that is lcall delay, after this line, definitely your processor will come, your controller will come in this specific line. Before coming, what your MUC will do, it will store the address of the next instruction somewhere. Okay, it will store the address of this instruction, because your MUC needs to know after executing this delay subroutine, where will it come back. So it needs to know. So it will store the address of this instruction. Then you come in this delay subroutine. This thing is very obvious. Your R5 contains the value 255. Then you come over here, you are in this loop for 255 times. Finally, when R5 becomes 0, you come over here, return. So when you execute return, or when your assembler encounters return, what happens is it pops out this address. I mean, the address of this instruction is popped out, and your MUC comes over here when it sees this return portion. Then again you do this moving and all. See this. After that, again you are calling lcall delay. So what will happen in the second time when you are calling the delay, your MUC will store the address of this instruction, and it will come over here. So you will execute this delay portion. Then when you encounter return, your MUC will automatically return in this particular instruction. You will understand more about return. I mean, how I just said that this address is stored, how it is stored, and all these things we'll see just in the next example. But still, for the time being, if you have any query, you can ask now. If there are any questions, please, you can ask now.
Could we have declared the delay subroutine earlier before the lcall?
Before the lcall? No, normally we declare it. I mean, there can be a backward jump, if that's what you are saying. I mean,
Yeah,
you are calling the, there can be backward also. Yeah, it can be done.
Okay.
The important thing about delay is, look at this first line. You need to specify from which address your delay subroutine is there. So that is very important.
Okay, sir.
Can you repeat the same back?
Can I repeat the?
Same after the second lcall delay, the next line. Can you repeat it again?
Okay, okay. So when we come over here, that is when we are in second lcall delay, the address of the next instruction, that is this one, short jump back, the address of this instruction is stored by the MUC. So you see this delay, you come over here, you execute this delay subroutine. Then when you encounter return, your MUC automatically pops out the address of this instruction, and it starts executing from this instruction. The only difference is, see, from when you are calling the first lcall delay, the address of this instruction is stored. When you are calling the second lcall delay, the address of this instruction is stored. So the main thing is, whenever you call delay, the address of the next line is always stored by the MUC. Is it okay now?
Sir. Yes, sir. Sir, what is the function of short jump back?
Thank you. Really thank you. I missed a level. There is another level over here. Thank you for that. Okay, so short jump back means we'll come over here and we'll keep doing this thing indefinitely. Sorry for that. There is supposed to be a level over here. Anything else? Okay, let us see the next example. For the next example, actually, I need to use MS Word. I think it will be better if I show you in MS Word. Okay, so I've already written the code in this way. I mean, it will take a lot of time for you to write. So I will suggest you no need to write. You already have the book, and this is example 3.9 of the book. And if you want, I will upload this Word file as well. So no need to write. What is new over here is, see, I have written the exact same code, the one that I have just written. This is the exact same code. I have only included the line number over here, and this is the value of the program counter. So these are the two things I have included, and of course you can see one column blank. So that is the column for your opcode. So let us see. First of all, let us analyze this program counter and opcode. After that, we will see other things. Starting for the first line, obviously you know there will be no opcode. For the second line, for moving something to register A, the opcode is 74. What will be there after 74? Can you finish the opcode?
55.
Good. It will be 55. For moving something to port A from register, to port 1 from register A, the opcode is F590. There is nothing to understand. This is straightforward instruction. Now let us see this one, lcall delay. So it is a 3-byte instruction, as we have already discussed. First byte is the opcode, so I'm telling you the first byte is 12. So tell me what will be the next 2 bytes. Let's see if you can find out. Try to see the class note, what is written, and then tell me what will be the next opcode. I mean, what will be the next 2 bytes of the opcode.
0300.
Very good. Exactly. Very good. It will be 0300. For the next one, it will be 74, and of course the value is there, so the value will come. The next one is again same, F590. After that, we have got another lcall. So definitely both the lcalls are exactly same, and will go to the exact destination. So the opcodes will also be same. Now look at a small thing. I mean, you need to be careful about this thing. The first opcode, it is a 2-byte instruction. So your program counter also incremented by 2. In the second one, again the opcode is 2-byte instruction. So again your program counter incremented by 2. Over here, this is a 3-byte instruction. So you see, it has incremented by 3. So be careful about these things. When you write your code, your program counter and opcode, they must be synced with each other. You can see in line number 9, there is nothing. It is a complete empty line, but still, if you had to write the value of program counter, what would be the value over here in line number 9? Try to apply whatever we have learned in the last class. If we had to write the value of program counter, frankly speaking, there is a value of the program counter, because your compiler does not know that this one is empty. So it will come over here, then it will see that it is empty. So definitely a program counter will be there. So what will be the value of program counter in line number 9?
Sir, 10.
Very good. Thank you. You know, these things makes me really happy. Okay, so let me say you how he calculated, whoever gave the answer. You see short jump. You know that the opcode of short jump is 2-byte sized. Okay. Okay. To give that example, let me erase this one. Okay. See this one in line number 7. We have got 000B, and you know that this is a 3-byte instruction. So what is the value of the next pointer? The value of the next program counter. The simple calculation with B, you will add 3. So if you add 3 with B, you end up getting E. Why you added 3? Because this is a 2-byte instruction. Now you know that over here you will have a 2-byte instruction as well. So if you add 2 with E, you will end up getting 10. So this is how we find the value of the program counter as well. Now for the short jump, if I tell you the first byte is 80, and you know that the second byte for short jump is the relative address. So tell me what will be, complete the opcode for me.
Sir, 0000.
No. Try again. First thing is it will be, short jump is 2 bytes. So your answer will contain only 1 byte. So what will be the value of that particular byte? You forgot the formula. Come on, the formula was there. It is very easy.
So is it 6, sir?
No, what is the formula? Just apply the formula and use your calculator. That's it.
10?
Not 10. Hey, the last was so blue. Okay, let me show you. It looks like you really forgot. Okay, let me write over here. Okay, assume.
So
Over-
F0?
Exactly,
Oh.
F0. Good. It will be F0. Okay, those who forgot, I'm showing you the calculation. Over here, assume you have got XX. Okay, so with XX, you add the following address. So what is the following address? 10. So you add 10 with XX. The result should give you the address of the label. What is the label? The label is back. So what is the address of back? The address of back is 00. So you write 00. Now solve it using the calculator. If you solve it using calculator, you will see that the value of XX is equal to F0. Have you understood now?
Yes, sir.
Yes, sir. But sir, can you please explain one more time why the address of line number 9 is 0010?
Okay,
Yes, sir.
why the address line number 9 is 0? Okay, if I remove this address, okay, look at line number 3. I've removed this address and I've told you the value of the program counter in this line is 2. Now what you have to do is, you know that these opcodes will be there in the program counter as well. These opcodes will play a vital role. So what happens? This 7455 will be stored. And what is the size of this opcode? It is 2 bytes. So you will need 2 bytes to store this 7455. That means the 1 byte will go to this 0000, another byte will go to 0001. If that is the case, what will be the next value of your program counter? Definitely this one plus the size of bytes 2. So 0 plus 2 will give you 2. So come over here. The address is 000E. And you know that this is a 2 byte sized instruction. So if you add 2 with E, you will end up getting 10. Is it
Okay,
understood
sir.
now?
Understood.
Okay. Over here also in line number 10, line number 9, 10, there will be no opcode. Now let us come to line number 11. The opcode is very straightforward over here also. It will be 7D and the value FF will come. So the value is there. Okay, now we have got another short jump. You know, DJNZ is also a kind of short jump. We have discussed it. If I tell you the opcode of the first byte is DD, then what will be the complete opcode? Apply this formula. Come on, apply this formula now. Tell me the answer.
02.
No, you made some.
Sir, FE.
Exactly, FE. Come on.
FE, sir.
How do you calculate? You take your calculator to the hex mode. Okay, then you do the calculation. All right, then we have returned the opcode for return is 22, and we are done with the code. We are done with this program counter and opcode. Now, I told you that whenever we execute, the address is stored. How it is stored? Actually, your stack comes into play. So by default, in this program, the value of stack pointer is not defined. So by default, the value of the stack pointer is 07. So where do you encounter first lcall? You encounter first lcall in line number 4. So come in line number 4. This is where you encounter the first lcall. So I have told you the address of the next instruction will be stored by the MUSI. So it is stored in stack. So if it is stored in stack, I have already drawn the stack over here. I'm only showing the first 3 bytes. So I have already drawn the stack over here. So tell me what will be the change in the contents of the stack after line 4? What will be there in address 08?
74AA
No.
0007.
Exactly, 0007. So your 08, the address 08 will contain the lower byte, that is 07, and 09 will contain the higher byte, that is 00. 74AA is the opcode, okay, and this one is the address, and your stack always stores the address. So that's why the value in this 0809 will be 00 and 07. And you see after the first L call, the value of the stack pointer will be 09. That means your one L call is like two push instructions, and that is what obviously happened over here. So if you execute two push instructions, your stack pointer increments by 2. So you see we have pushed two values over here. So that's why your stack, the value of SP became 9. After that, you come in this delay subroutine, that is line number 11. You execute all this line. When you are in line number 13, you execute return, and return is like two pop instructions. That means these two instructions are popped out, and it will give the address where the MUC should go next. Since it is equivalent to two pop instruction, the value of SP will once again become 7. Have you understood up to this?
Yes, sir.
No,
If you have,
sir.
okay, those who have not understood, still now try with me. After line number 7, now come to line number 7, there is the second L call. Okay, so after this return instruction, the value of stack pointer again becomes 07. If that is the case, after line number 7, what will be the contents in stack? What will be in 08 and 09? Tell me. After line number 7,
So 0E
0E and then
00
00. And what will be the value of stack pointer?
9.
Exactly, 09. So then again you will come over here in delay subroutine. Then when you encounter this return, it is like popping out twice. So these two addresses will be popped out, and your stack pointer will be decremented to 07 once again. Okay, now if you have any question, which portion you did not understand, tell me, I'll repeat again.
Sir, I don't get the part that when the initial value of stack pointer is 07, why it is going to line 4?
Why it is going to line 4? Now I'm having confusion regarding your question. Repeat your question. Let me hear your question again.
Sir, L call operation here, sir.
Hmm.
It is like what operation here? Because I don't get why stack pointer value of 07 it is going to that kind of that line.
I mean, why stack pointer is becoming 09? You did not get this
No,
portion.
sir. I get the all the part, but I didn't get the initial part.
Okay, what happens when you call, when we execute line 4? This portion you did not understand.
Yes, sir.
Okay. So when we are in this line, I mean line number 4, you are calling this delay subroutine. So what will happen after line number 4? Your assembler will directly go in line number 11. So what you are doing, you are transferring the control to this line. You were in line number 4, but with this instruction, you are transferring the control to line number 11. That means in this line. Then you will execute line 11, you will execute line 12, you will execute line 13. After finishing line 13, you will again get back to line number 5. Did you get your answer?
Yes, sir.
Okay. Did you miss first portion of the class? I mean, today's class.
Yes, sir. My internet,
Maybe.
I was having trouble.
Okay, it's okay. So delay, I mean, L call means you simply call a subroutine. Okay, and how we can understand subroutine? In every subroutine there must be a return instruction. So you see over here, this is a delay subroutine. In this delay subroutine, we have got a return instruction. So that's what makes it a subroutine. Okay, so using call, it may be L call or A call. Using call instruction, we call different subroutines. So did all of you understand this example? Okay, if you do not have any question, I mean, this is the fastest I have finished explaining 3.9 among all the sections. The other sections took a lot of time to understand this example. So I don't know whether you understood or not, but again I'm asking, if there is any question, please you can ask.
Sir, you can move on.
Okay. What do you see in your screen now? The same thing, example 3.9.
Yes, sir.
Okay. Just a second, give me a second. What will happen is, so you understood this call instruction. Now we will try to incorporate push pop within a subroutine. Then we will try to analyze the stack. Okay. So things will get more and more interesting from this point onwards. Okay, I'm sharing my screen again. This is your example 310. I have already written it, so no need to write. It will take a lot of time if you start writing. It's quite a big code. So again, you have the book, so no need to write. Just look at the code. It is almost a similar code. The only difference is now we have got op instructions. So, okay, let us see the opcode first. Did I get distorted for last few seconds?
Yes, sir.
So I was saying that before we go to this push pop instruction, let us see the opcode. After finishing this opcode, then we will go for push pop instructions. So the first opcode is very easy, 7455. The next one is also known to you, F590. After that, it will be 7C99. Then it will be 7D, and the value will be 67. After that, we have got L call. It has the same address, so it will have the same opcode. Then we are moving some value to register A. It is 74. The value is AA, so it is 74 AA. Again, we are moving something to a port. Then it is F590. Again, we are calling the delay 120300. Tell me the opcode for this one. It will be 80, and after that, finish the opcode for me.
EC.
EC, sir.
Exactly. It will be EC. Now moving on, no opcode in this line or in this line. Over here, we'll have an opcode. So the opcode for pushing something is also 2 byte. The first byte is the opcode. The second byte is the direct address. So what are you pushing? You are pushing address 4. So it will be C004. In the next one for pushing again, the opcode is C0 and then followed by direct address. So the address is 05. Now we are moving something. So it is 7C and the value itself. So 7CFF. After that, again, it will be 7D and the value itself, that is FF. Let's see, finish it. DD. After that, this is also a short jump. So what will be the address?
FE.
Good. FE. After that, we have got DC. What will be the address now?
FA.
FA. Thank you. Then we have got pop. For pop, it will be a similar instruction. So the opcode is only different, D0, but it will be followed by the exact address. So the address is 05. So definitely this one will be D004. And you already know the opcode for return is 22. We are done with the opcodes. And you can check the program counter. It is in sync with the opcode. Now let us analyze the stack. So again, in this program also, the stack value is not defined. I mean, the value of stack pointer is not defined. So we will assume the default value, which is 07. After the first L call, tell me what will be there in 08. After the first L call, what will be there in 08?
0B.
Good, 0B. What will be there in 0B? Yeah, what will be there in 09?
00.
Good, 00. What will be the value of stack pointer?
9.
09, exactly. You see, after the first L call, I mean, here is your first L call. After the first L call, you come in line number 13. So the first instruction that you encounter after the first L call is push 4. So tell me, what will be the change in the contents after push 4? Okay, let me write over here 0B because it will remain like this. Okay, so tell me what will be the change in the stack after push 4?
At 0A it will be 04.
0A will be
04 maybe.
no. Try to think again. You can see your previous class notes. What happens when you push a register? What happens? When I write push 4, what happens actually? Come on, you should be able to answer this.
99H.
99H, exactly. It will be 99. What happens when you write push 4? So whatever is there in address 4 will be pushed to the next stack. So what is address 4? You see nothing has been said about your PSW. So you will assume register bank 0. In register bank 0, in the address 4, we have got R4. So what is the value of R4? The value of R4 is 99. So definitely after push 4, the value 99 will go in this address 0A, and the value of your stack pointer will also be incremented by 1. So it will become 0A. So what happens after push 5? The previous things will be like this: 0B, 00, 99. What will be the change? What will happen after push 5? Come on, now you should be able to answer.
67.
Exactly. Now it will be 67. And the value of your stack pointer is
0B.
0B. Okay, after that, we execute this line. This line. Then we execute this line. Nothing will happen in the stack. We are only interested in the stack. Then this line, then this line. In all these cases, nothing will happen in stack. When you write pop 4, what will happen is this 67 will be popped out and it will be stored in register R5. And the value of your stack pointer will be decremented by 1. So you will come over here in this column. You will see this figure there. After pop 4, this 99 will be popped out and it will be stored in register R4. And the value of stack pointer will also be decremented by 1. So you will see the scenario of the first two columns. After that, you execute return. If you remember, return is like two pop instructions. So this instruction will be popped out and your MUSI will get back to this address, that is 000B. And again, your stack pointer will become 07. Okay, the floor is open for questions. This is your example 310. You either ask questions or you can stay quiet and not understand anything.
So can you say why a return instruction is like two pop instructions?
Okay. Return instruction totally depends which call instruction is calling. If you have a L call, your return instruction is like two pops. If you use A call, your return instruction is like one pop. It totally depends is when you are calling, your call is equivalent to how many push instructions. So in this L call, you have got 2 bytes of address that you need to save. So in order to save 2 bytes of address, you need L call and you need 2 push, because you cannot save 2 byte address in the same push. So that's why L call is equivalent to 2 push. So if you have 2 push, there must be 2 pops to balance it out. That's why if L call takes 2 push, your return will also take 2 pops. Try to understand over here. Over here in this line, we have got a push instruction, then we have got a 2 push instructions. See, before these pop instructions, if your return instruction was executed, you would get a wrong result, because that would not make any sense. After these 2 push instruction, if you give your return instruction, then these 2 values would have been popped out, which is wrong, because you want to pop out these 2 values. So every push instruction must be balanced by equal number of pop instruction. Otherwise, your stack will start giving you wrong answers. Did you get the point?
Yes, sir.
Okay, any other question? Go on.
Sir, what is happening after pop 5 and pop 4?
What is happening after pop 5 and pop 4? Try to understand. When you come in this line, can you tell me what is the value of R5 when you are in this line? When you are in line number 19, what is the value of R5? Can you guess?
67.
No, not 67. Look at the previous lines. Look at line number 15, 16.
0.
Exactly, 0. When you come to line number 19, the value of R5 is 0. So what happens when you write POP5 is
Why 0, sir?
why it is 0. Look at this one. Look at these two. These two are forming a loop. So you will decrease R5. How long will you decrease? As long as R5 does not become 0. When R5 becomes 0, you come to this line. That is line number 18. And how long will you be in 18? You will be in 18 as long as R4 does not become 0. Only when R4 becomes 0, you come to line number 19. So what was the condition of coming to line number 18? The condition of coming to line number 18 was that R5 has to be 0. What is the condition of coming to line number 19? The condition of coming to line number 19 is R4 has to be 0. That means when you are in line number 19, the values of both R5 and R4 are 0. Did you understand now?
Yes, sir.
Okay. Now, when you are popping out, when you pop 5, this value, that is the topmost value in the stack, will be popped out. How do you understand this is the topmost? Because it depends on the value of the stack pointer. Okay. So the topmost value of the stack will be popped out and it will be stored in address 5. If you recall your previous classes, address 5 means register 5 in bank 0. So that's why after pop 5, your R5 will again contain the value 67 that you initially stored. Then again, after pop 4, by the same logic, now the value of stack pointer is 0A, which is the topmost value. So 99 will be popped out and it will be stored in the address 04. And 04 is R4 in bank 0. So you will give, you will put R4 the value 99 which you previously stored. Is it clear now?
Yes, sir.
Okay, anyone else? Any other question? Don't just think, don't just sit and think that the question that I have in my mind might be a bit silly. So let me not ask. Please do not have this intention in your mind. Whatever question you have, you should ask. Only then you will learn. Okay, you have come here to learn. So there is no, what I can say, shame in asking questions. You should come out of that mentality. Anyway, so no more questions. So I'll move on. So I'll stop sharing and I will get back to the whiteboard. Let us now focus on time delay. And so far we have been seeing a lot of delay subroutines, but still we do not know how to calculate the exact delay in seconds, right? We can say that we are calling a subroutine delay subroutine. We can go loop within loop, and in this way we can increase the delay, but still we do not know how to calculate the exact, how to calculate in seconds what is the exact delay. So now we'll see these calculations, okay? How to calculate the delay in seconds. These things are pretty straightforward, theoretical. Nothing much to discuss. It takes a certain number of clock cycles to execute an instruction, and these cycles are referred to as machine cycles, and it totally depends on the crystal oscillator connected. You guys are section B. So one of your sections did the lab. So those who did the lab, you already know that we connect a crystal oscillator. So the other section you will come to know tomorrow, inshallah. And the last thing is, in your 8051, one machine cycle lasts for 12 oscillator periods. So this 12 is it has a vital meaning. For calculating the exact time period, you need to know this information. That is, one machine cycle lasts for how many oscillator periods. So over here we see that one machine cycle lasts for 12 oscillator periods. So let me show you a numerical example. There you will understand that how to calculate. And as I said, this 12 will play a vital role in that calculation. Have you finished writing this portion?
Yes, sir.
This is example 313 of the book. You can see your book also if you want. Okay. The question is, we have been provided with 3 crystals. Okay, the specification is, the first crystal is 11.0592 megahertz. The second crystal is 16 megahertz, and the third crystal is 20 megahertz. So the question now is, calculate the time period of each machine cycle in these 3 cases. So let us begin with the first one, how to calculate. So if you remember, one machine cycle lasts for 12 oscillator periods. So that means right at the start, you will divide this frequency by 12. So write megahertz and divide it by 12. So that will give you the frequency of one machine cycle. Okay, 921.6 kilohertz. If you use calculator, you will get this result. This is the frequency of one machine cycle. If that is the case, what is the time period of one machine cycle? Let's see, you can calculate. I'm telling you that the frequency of one machine cycle is 921.6 kilohertz. So now tell me, what is the time period of one machine cycle?
1.08 microseconds.
1.08 into 10 to the power minus 3.
1.08
into 10 to the power minus 3.
Minus 6.
Minus 6.
So minus 6.
Exactly, minus 6. 1.08 into 10 to the power minus 6. Okay, to be specific, 10 to the power minus 6 is microsecond. Those who answered, tuition karo nahi? Yes, no?
Yes, sir.
Okay. That was expected because I myself forgot the formula. Okay, when I was taking preparation. Okay, the formula is, sorry, not this. The formula to calculate this is, your frequency is equal to 1 over time period. Okay, so if you are given the time period or frequency, you can calculate the opposite one by this formula. So you are given the frequency, so the time period is simply 1 divided by 921.6 kilohertz. Okay, in this formula you will get the answer. If I go to the next one, what is the time period? Tell me.
7.510 inverse 7 seconds.
Okay, we can write 0.75 into 10 to the power minus 6. That is 0.75 microsecond. So give me the last answer in microsecond.
0.6 microseconds.
Exactly, 0.60 microsecond. Is it clear to all of you? If there is anyone who did not understand, you can tell me. I will show you the calculation of B or C. But please make sure you understood this thing. Okay, no question means I'm
Sir, we have to divide by
Hmm,
2 or 12.
12. Thank you. Definitely we have to divide by 12. Okay, so what did we find? We found out the time required to execute one machine cycle. So in your MUSI, if you, I mean, in most of the cases, we connect this crystal, okay, this frequency. So that means your MUSI, in most of the cases, it takes about 1.085 microsecond to execute one machine cycle. Okay. Still, we have not learned how to calculate the delay. So now let us see a concrete example. This one is example 315. Again, it is the same one as your book. So if you don't want, you may not write. So we start with origin 0, then we have some code, then we call delay. Then again, we have some code, doesn't matter. We are only interested in the delay portion. Okay, so we'll forget about everything. So let me just write the delay subroutine. So say the delay subroutine move looks like this. Move R3, 200. Here, and since it is a subroutine, there must be a return instruction. Now you need another information to find out the exact time delay. That is, you need to know the machine cycle. For the time being, let me just tell you the machine cycle for executing this move instruction is 1. For this DJNZ, the machine cycle is 2. For this return also it is 2. How I found this machine cycle, I will tell you a bit later. And say you are given this information that the frequency of the crystal oscillator is 11.0592 megahertz. Okay, these are the information which are given to you. Now let us find the solution. So if you are given the frequency of the crystal oscillator, definitely you can find the time period of one machine cycle. So what is the time period of one machine cycle?
1.085 microseconds.
Exactly, 1.085 microsecond. So see, this is the time period for one machine cycle. So you need this information and you need the number of machine cycle. So now you have all the information. So can you calculate how much delay we are generating in microsecond using this delay subroutine? What is the answer? Try to find the answer on your own.
5.425.
So 5 multiplied by 1.085.
5.425.
It is actually a little bit complicated than this. It is not that simple that 2 plus 2 plus 1, 5, multiply 5 with 1. See the code again. Try to understand the code again. I know at least some of you can answer.
Sir, for 200 loops, sir, we multiply. Sir.
You tell me the answer first. I will hear the calculation later.
Sir,
Is it like 435 or something like that?
sir, 217, sir.
It's 437.255 microseconds.
Exactly, 437.255 microsecond. Good. Okay, now let me show you how we found out. Okay, how we found this answer. Okay, how we found this answer is, look at this first line. Delay move R3 200. Okay, so how many times will this line be executed? As of now, this line will be executed only once. So we'll have only one machine cycle. Now come over here. DJNZ R3 here. That means you will stay in this line for how many times?
200 times.
Exactly. So your machine cycle will be 200 into 2 because 200 times you will execute this line. So definitely your machine cycle will be 200 into 2. And then you will come to return how many times you will execute. You will execute it just once. So machine cycle will be 2. If you add this, what is the total machine cycle?
403.
Yeah.
403.
Exactly. I had 203. Sorry, yeah. 403. So how do you calculate the delay now? So now 403 multiplied by 1.085 microsecond. Whatever answer you get, that is the result. In the book, I think the answer given is 436.255. This type of deviation is totally acceptable in this delay, because see the delay you are calculating in microseconds. So if there is a deviation of 1 microsecond, it doesn't matter. 1, 2, 3, 4, 5 microseconds doesn't matter. As long as your approach is correct, you do the calculation using your calculator, whatever you get, that is the right answer. So in this case, I think you do get 437.255. So now if I give you any loop, I believe all of you can find the exact time delay, isn't it?
Yes, sir.
Okay, so now one question is still there. How did I find this machine cycle? Let me show you. Let me give me some time to open it.
So I have a question, sir.
Wait, I'll get back to your question after this. Don't worry, I'll give you time for questions. Everyone, can you see my screen? Can you see that I have a table in front of me? Is it visible? Come on.
Yes, sir.
Yes.
So this is your table A1 of the appendix of your book. The soft copy that I have provided, it is page 554 of the soft copy of the book. So you really need to know the information from this table to know the machine cycle. But still, look at your class note. You need to understand a few things over here. Look at the class note. The first instruction was move R3, hashtag 200. So if I zoom in a little bit, you can see I have got a lot of move instructions. So you need to understand which move instruction did you actually use. We actually used this move instruction, that is move Rn, hashtag data. Rn means the value of n can be from 0 to 7. So if you move any data directly to the register, the machine cycle is 1. So this is how we get the machine cycle from the table. The next instruction was DJNZ. So keep scrolling down. Over here you can see DJNZ. So DJNZ are registered, then the label. So the machine cycle is 2. So from here I got the machine cycle is 2. The last instruction was return. You can see return, the machine cycle is 2. So now the most obvious question that should come in your mind is, sir, whether should we memorize this table? The answer is no. You don't have to memorize the table. In your exam, if I set any question that needs the use of this table, then either I will provide the table or I will provide you with the necessary information. The bottom line is you don't have to memorize the table, but you need to understand how you can find out your specific instruction or a specific mnemonic from this table. Like the example I just showed you. There are a lot of mnemonics for move, but you need to know which one you will use. So you need to understand that, but you don't have to memorize it. So this is there in your page 554 of the soft copy. You can see that. Actually, I got the soft copy of the book from one of your friends. Okay, I assume that all of you have, but then I saw that some of you still don't have the soft copy. So that's why I uploaded this soft copy. Okay, getting back to the whiteboard, someone had a question. Okay, so what is your question? Say.
My question was that how to know the machine cycle. So answer.
See, that's why I told you that. Wait, let me finish then ask question. Okay, any other question? Any other question? Anyone? Okay. If there are no other questions, this is the last example that I was supposed to show you of chapter 3. So with this, your chapter 3 comes to an end. There are many other examples in chapter 3. Please go through those examples. All those are actually very easy. So please go through the examples. And from the next class, inshallah, we will start chapter 4. Okay, so let me just take your attendance. After that, I'll let you leave. Section B, right?
Yes, sir.
You are supposed to be only absent. A lot of you are absent. So your total students should be 53. I see you have got 48. So that means 5 of you are absent. Should I take the attendance or you can tell me the ID?
So 147 of 16 batch.
Oh, ওটা তো কম, wait. Yes, 147 of 16 beds. আচ্ছা, সিআর কে
Yes, sir.
কোনো আপডেট আছে এই ছেলেটা সম্পর্কে? ও তো কোনো ক্লাসও করতেছে না, ও ল্যাব মনে হয় কালকে। ও কি ল্যাবও করবে না?
স্যার উনি মানে ক্লাসে একটু কম আসে।
ক্লাসে
But
একটু
for
কম
the-
আসে। আচ্ছা, আমি একটা জিনিস বলি, হ্যাঁ তোমাদেরকে। Okay, you stay back. I'll tell you at the end. Okay, who are the other people who are absent? I've got 1, 4 to go. Who are the other 4?
স্যার আইডি 55
ID 55. Yeah, oh, Mudibul Aji. Mudibul Aji নামটা নাম কি? Okay, I have to check. Okay, then I've got 2. Someone joined just now. Who is that?
Sir, it's 99.
এতক্ষণে জয়েন করলা নাকি ডিসকানেক্ট হয়ে গেছিল?
না স্যার আমার ডিসকানেক্ট হয়ে গেছিল, কারেন্ট চলে গেছিল, পরে আমি ফোন দিয়ে জয়েন করলাম স্যার।
আচ্ছা, ওকে। Okay, so who are the rest 3? Not rest 2. আর দুইজন কে? Come look for the following student ID, please. I don't want to take the attendance again. It will take a lot of time. আর দুইজন absent, still 2 are absent. Who are those? (1085). Are you present?
Yes, sir.
Okay, you were absent in the last class, so that's why I said. Okay, who are the other 2? Please come on, help me out over here.
Sir, maybe 55.
Sir, I was present, sir. I got disconnected. That's why I couldn't give the attendance. I gave the quiz, sir.
Last class you were present.
Yes, sir.
Okay, so if you get disconnected like this, কত 1085 na?
Yes, sir.
So if you get disconnected like this, you need to inform your friend, okay, so that they can say that yes sir, I saw him or something like that. Acha, yeah, 055 is absent. Who is the other one?
So 149 probably.
055 তো already mark করছি। আটা কত 149 149. Okay, I still need another one who is absent. I've got 3. Please look for the following student ID. If you look for your friend, you will find it. আচ্ছা, এখন যার আইডি পাবো তার আগের আইডি কে অ্যাকসেপ্ট করব if I take the attendance. Remember, whose ID I find, I will mark absent the previous ID as well. Okay, respond to your IDs, please. 16 batch 035. Yeah, just raise your hand. Good. Okay, you can just raise your hand. 17 series 009. Then 13. 16. 33. 34. 48. 51. 53. 54. 55. So 55 is absent already. 56. 57. 61. 62. 64. 67. 69. 70, 72, 73, 74,